Look up. Step outside on a clear, moonless night, far from the ceaseless glare of human cities. Let your eyes adjust to the deep velvet blackness. What you are witnessing is not a static painting. It is not a snapshot of a single moment in time. The spectacle above is a time machine of impossible scale. Every single pinpoint of light you see is a ghost, a phantom message sent from a distant past. Some of these luminous couriers began their journey when civilizations were first rising on Earth. Others departed before humanity even existed. We live under the illusion of a universal now, a comforting fiction that everything we perceive is happening at the same instant we perceive it. But the cosmos operates on a different schedule. The universe does not grant us the luxury of the present. Instead, it offers us a profound, silent museum of history. To navigate this museum, to understand the true chasm that separates us from these celestial embers, we needed a new kind of measurement, a yardstick so immense it could span the terrifying emptiness and make sense of the incomprehensible. We call it the light year, and it is a unit of distance that does more than measure. It fundamentally breaks our brains. It shatters our terrestrial intuition and forces us to confront the sheer, soul-crushing, and magnificent scale of everything. To begin, we must comprehend the messenger itself, light. It is the universe's absolute speed limit, a cosmic constant, decreed by the laws of physics. Its velocity in a vacuum is staggering, almost mythical, roughly 300,000 kilometers, or 186,000 miles per second. Let's try to cage this speed with an analogy. Imagine a racetrack wrapped around the equator of our planet. A beam of light, a single photon fired from a starting pistol, would complete that circumnavigational lap, not once, not twice, but more than 7 times in the blink of an eye. In the time it takes for a human heart to beat just once, that pulse of energy could travel to the moon and back. This is a velocity so extreme it defies our experience. The fastest machines we have ever built, our deep space probes, hurling through the solar system, are like stationary objects. Compared to the sprinting pace of a photon, our comprehension falters at such a scale. Now, imagine that impossibly swift messenger, light, traveling without pause, without rest, for an entire year, for 365 days, 8,760 hours, over 31 million seconds. It streaks across the void. The distance it covers in that time is a single light year. In terrestrial numbers, this is almost meaningless. It's approximately 9.46 trillion kilometers, or 5.88 trillion miles. The number is so colossal, so detached from human reality, that it becomes an abstraction. A human lifetime of 80 years contains about 2.5 billion seconds. If you were to count 1 kilometer for every second of your life, you wouldn't even come close to the distance light travels in a year. You would have to live over 3,000 lifetimes just to count out the kilometers in 1 light year. This is the fundamental yardstick of the cosmos. It is a measure born not of convenience, but of necessity. For centuries, the stars were just ethereal fixtures, glued to a celestial sphere of unknown dimensions. We could measure their positions, their brightness, their color, but their distance? That was a question for gods and philosophers. The first heroic attempts to stretch a measuring tape into space came from the ancient Greeks. Thinkers like Aristarchus of Samos used the elegant logic of geometry to make audacious calculations. By observing the angle between the sun and a half-lit moon, he tried to determine the ratio of their distances from Earth. His methods were brilliant, but his tools were too crude. His results were wildly inaccurate, yet the ambition was monumental. It was the first flicker of a profound human impulse, to know our place, to measure the abyss. For nearly 2 millennia, that abyss remained immeasurable. The stars remained tantalizingly beyond our reach. The breakthrough required a concept as simple as it is profound. Parallax. Hold your thumb out at arm's length. Close your left eye and line your thumb up with a distant object. Now, without moving your thumb, close your right eye and open your left. Your thumb appears to jump, to shift its position against the more distant background. That apparent shift is parallax. The secret lies in the distance between your two observation points, your eyes. The farther away your thumb, the smaller that jump becomes. Astronomers realized that Earth itself offered two observation points. As our planet orbits the Sun, our vantage point on the cosmos shifts by a staggering 300 million kilometers, or 186 million miles. Surely, from one side of our orbit to the other, the nearest stars must appear to shift, just like our thumb. The theory was sound. The execution, however, was a nightmare. The stellar parallax shift was predicted to be minuscule, an angle so vanishingly small it would be like trying to measure the width of a human hair from miles away. For centuries, the world's greatest astronomers tried and failed. Their instruments were not precise enough. The stars, it seemed, were simply too far away. The failure to detect parallax was even used as an argument against the idea that the Earth orbited the Sunday. This immense challenge fell to a German astronomer named Friedrich Bessel. In the 1830s, using a state-of-the-art telescope called a heliometer, Bessel dedicated himself to this maddeningly delicate task. He chose a faint star in the constellation Cygnus, called 61 Cygni. It was chosen not for its brightness, but for its speed. It moved across the sky faster than its neighbours, a characteristic which suggested it might be relatively close. Night after night, month after month, Bessel made his painstaking observations. He was in a race against other astronomers across Europe. He measured the star's position in July, then again in January. 6 months later, when the Earth was on the opposite side of the Sunday, he was hunting for a wobble, a tiny, almost imperceptible displacement, dwarfed by atmospheric distortion, temperature changes in his instruments, and the sheer difficulty of the task. Then, in 1838, after years of meticulous work, he found it. He had measured a parallax shift of just over 1/3 of an arcsecond. An arcsecond is 1/3600th of a degree. It is an impossibly small angle. But from that tiny measurement, using simple trigonometry, Bessel calculated the distance to 61 Cygni. His answer was about 10.3 light-years. It was a watershed moment in human history. For the first time, we had touched a star with our minds. The celestial sphere was shattered forever. The universe was revealed not as a ceiling above us, but as a three-dimensional ocean of unimaginable depth. And Bessel's number, 10.3 light-years, was terrifying. The closest stellar object we could measure was 100 trillion kilometers away. Our own solar system was revealed to be a speck of dust, an isolated island in an ocean of emptiness. The parallax method was a triumph, but it had its limits. Like holding your thumb farther and farther from your face, the parallax shift of more distant stars becomes too small to measure. It could only provide distances for our closest cosmic neighbours, a few hundred stars within our local bubble of the Milky Way. To plumb the deeper, darker waters of the cosmic ocean, we needed a new tool. We needed to build a ladder. This construct, known as the Cosmic Distance Ladder, is one of the greatest intellectual achievements of our species. Each rung on the ladder allows us to measure farther into space, and each new rung is calibrated by the one below it. The foundation, the very first step, is parallax. The next rung on this ladder was discovered not in a grand observatory by a celebrated professor, but in a quiet room by a woman whose name was almost lost to history. Her name was Henrietta Swan Leavitt. In the early 1900s, she worked at the Harvard College Observatory as a human computer, one of a team of women tasked with the laborious job of examining photographic glass plates of the sky. Her job was to catalogue stars, measuring their brightness and position. Leavitt was assigned to study a specific class of star, known as a Cepheid variable. These are peculiar, pulsating stars. They rhythmically swell and shrink, growing brighter and then dimmer with a precise, clockwork regularity. While studying thousands of these stars in the Magellanic Clouds, two small satellite galaxies of our own Milky Way, Leavitt noticed something extraordinary. She found a direct, unmistakable relationship between the period of a Cepheid's pulsation, how long it took to go from bright to dim and back again, and its intrinsic brightness. The longer the period, the more luminous the star truly was. This was a discovery of monumental importance. Imagine you are standing on a dark coast, looking out at a sea filled with lighthouses. You see some lights that are bright and some that are faint. The faintness could mean two things. Either it is a weak, low wattage bulb that is close by, or it is a tremendously powerful beacon that is very far away. You cannot tell the difference. But what if you knew that all the lighthouses with a slow, 5-second flash cycle were powerful 1000 watt bulbs, and all the ones with a rapid 1-second flash were weak 100 watt bulbs? Suddenly, you have a code. By timing the flash, you can know the lighthouse's true wattage. And by comparing that true, intrinsic brightness with the apparent faintness you see from the shore, you can calculate its exact distance. Henrietta Leavitt had found the universe's secret code. Cepheid variable stars were cosmic lighthouses. They were standard candles. Her discovery provided the second rung of the ladder, a tool that could measure distances far beyond the reach of parallax. This new tool soon fell into the hands of an astronomer named Edwin Hubble. In the 1920s, a great debate raged in astronomy. Were the faint, spiral nebulae we saw in our telescopes small clouds of gas within our own Milky Way galaxy? Or were they, as some suspected, immense island universes, entire galaxies just like our own, separated from us by unfathomable distances? Using the mighty 100-inch Hooker telescope at Mount Wilson, Hubble hunted for Cepheid variables within the largest of these smudges, the Andromeda Nebula. He found one. Then he found another. He carefully measured their pulsation periods. Using Leavitt's law, he performed the calculation. The result was breathtaking. Hubble calculated that the Andromeda Nebula was nearly 1 million light-years away. Modern measurements have refined this to 2.5 million light-years. It was not a cloud inside our galaxy. It was a sibling galaxy, a colossal structure containing hundreds of billions of its own stars, floating in the void. In that moment, the known universe expanded 100-fold. Our Milky Way was not the universe. It was just one galaxy among countless others. The light year had transformed from a measure of stellar distance to a measure of intergalactic emptiness. The scale was already becoming mind-numbing, but the ladder was not complete. Cepheids, as brilliant as they are, become too faint to be seen in the most distant galaxies. To see to the very edges of creation, we needed an even brighter candle. We needed a standard candle so luminous it could outshine an entire galaxy, if only for a few weeks. We needed an exploding star, specifically a Type Ia supernova. This cataclysmic event has a very particular origin story. It begins with a small, dense, dead star called a white dwarf, the remnant core of a star like our Sunday. If this white dwarf is in a binary system with another star, it can gravitationally siphon material from its companion. Slowly, year after year, it accumulates this stolen mass. The white dwarf grows heavier and heavier until it reaches a precise, critical threshold, about 1.4 times the mass of our Sunday. This is known as the Chandrasekhar limit. At this exact point, a runaway thermonuclear reaction ignites in its core. In a fraction of a second, the entire star detonates in an explosion of unimaginable power. Because every Type Ia supernova is triggered at the exact same mass, the resulting explosion is remarkably consistent. They all reach almost the same peak luminosity. They are the universe's standardized bombs. A Type Ia supernova is a standard candle of the highest order, 1 billion times more luminous than our Sunday. They are so brilliant, they can be seen from halfway across the observable universe. By hunting for these fleeting, spectacular detonations in distant galaxies, astronomers forged the next rung of the distance ladder. They could now measure not just millions, but billions of light years. And when they did, they discovered something that would change our understanding of reality itself. They expected to see the expansion of the universe, a legacy of the Big Bang, slowing down due to gravity. Instead, they found the exact opposite. By using these supernovae to measure the vastest distances, they found that the most remote galaxies were moving away from us, slower than they should be. This meant that in the past, the expansion was slower. Today, the expansion of the universe is accelerating. Some unknown force, a mysterious dark energy, is pushing the fabric of space-time apart, faster and faster. This Nobel Prize-winning discovery was made possible only by our ability to measure distances on the scale of billions of light years. The final rung of the ladder takes us to the very edge of sight. It builds upon another of Hubble's discoveries, redshift. Just as the sound of an ambulance siren changes pitch as it moves towards or away from you, the color of light also changes. Light from an object moving away from us is stretched, shifting its wavelength towards the red end of the spectrum. Hubble and his colleagues found that the more distant a galaxy, the greater its redshift, the faster it was receding from us. This relationship, now known as the Hubble-Lemaitre law, became the ultimate ruler for the cosmos. By measuring the redshift of a galaxy's light, we can infer its velocity and, from that, its distance. It is this method that allows us to estimate the distance to the most ancient and remote objects our telescopes can detect, galaxies whose light has been traveling towards us for over 13 billion years. And so, we stand at the top of the ladder. We have surveyed the landscape. Parallax gives us our neighborhood. Cepheids map out nearby galaxies. Supernovae chart the cosmic continents. Redshift takes us to the horizon. We have measured the universe. But it is here, armed with this knowledge, that our brains truly begin to break. The light year is not just a unit of space. It is a unit of time. They are inextricably fused. When you look at the sun, do not look directly. The light striking your eye left its surface 8 minutes and 20 seconds ago. If the sun were to vanish instantly, we would remain blissfully unaware for over 8 minutes, basking in the glow of a star that was no longer there. When Jupiter is at its closest to Earth, the light we see is over 30 minutes old. We are seeing it as it was half an hour in the past. The light from Proxima Centauri, our nearest stellar neighbor, is 4.2 years old. When we observe it, we are seeing it as it was 4.2 years ago. Any message we send it, traveling at light speed, will take 4.2 years to arrive. Their reply will take another 4.2 years to return. A simple conversation would take longer than a human childhood. This temporal chasm grows ever more profound. The light from the star Vega is 25 years old. If a civilization there were looking at Earth with a super telescope, they would not see us in the present. They would see our planet as it was 25 years in the past. The light from Polaris, the North Star, is over 430 years old. It began its journey to your retina around the time of Galileo. The star Deneb in the constellation Cygnus is some 2,600 light-years away. The photons arriving tonight departed when the prophet Jeremiah was writing, when the city of Rome was a young kingdom, and we are still in our own backyard. Let's return to the Andromeda Galaxy, our magnificent neighbor. Its light is 2.5 million years old. When that light began its inexorable journey across the intergalactic void, our ancestors, early hominids like Time's Australopithecus asterisk, were walking the plains of Africa. Modern humans did not exist. The image we see of Andromeda tonight is a prehistoric photograph. We have no idea what it looks like now. It could have changed dramatically in the intervening eons. For all we know, it could be gone. We wouldn't find out for another 2.5 million years. This shatters our concept of a shared present. The night sky is not a window, but a time capsule. Each star is a different chapter from a different epoch. There is no is, only a collection of was. Our universe is a patchwork quilt of disparate pasts, stitched together by the finite speed of light. Our perception of simultaneity is a profound and provincial illusion, a trick of our minds born from living on a tiny world where light speed seems instantaneous. This realization also brings with it a deep and chilling sense of isolation. The light year reveals the universe to be defined not by its contents, but by its emptiness. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of over 430,000 miles per hour. Even at that blistering pace, it would take it over 6,600 years to reach Proxima Centauri. Generations would live and die aboard a ship on such a journey. The distances between stars are so vast that they function as near-perfect prisons, isolating solar systems from one another for cosmic timescales. And the distances between galaxies are another level of lonely entirely. If our Milky Way galaxy were the size of a dinner plate, the Andromeda galaxy would be another dinner plate, over 20 feet away. In between is almost nothing, a few stray atoms per cubic meter, a perfect vacuum. This emptiness is expanding. Dark energy is stretching the fabric of space itself. This leads to a final, mind-bending paradox. The universe is 13.8 billion years old, so you might think that the farthest we could possibly see is 13.8 billion light-years away. But that's not right. The current edge of the observable universe is estimated to be about 46.5 billion light-years in radius. How can this be? Imagine an ant walking along a rubber band that is being stretched. The ant is walking at a constant speed, but the distance it has to cover is constantly increasing. In the same way, the light from the most distant galaxies has been traveling through a universe that has been expanding for its entire journey. The space that the light has had to cross has itself been growing. So, an object that was much closer when it emitted the light is now, at the present moment, much, much farther away. And this expansion is accelerating. Galaxies beyond a certain distance, known as the cosmic event horizon, are now receding from us faster than the speed of light. This does not violate relativity, because it is not the galaxies themselves, moving times through time's space, but space itself that is expanding. The light from those galaxies will now never reach us. They are forever lost to us, their information erased from our future. Project this into the far future. In 100 billion years, the acceleration will have carried every single galaxy outside our own local group of gravitationally bound galaxies. Beyond this cosmic event horizon, the night sky for a future civilization will be almost entirely black. They will see the stars of their own Milky-Way supergalaxy, the merged form of the Milky Way and Andromeda. But beyond that, nothing. No faint smudges of distant galaxies, no evidence of a wider cosmos, no cosmic microwave background radiation. They would be adrift in a void with no way of knowing that a universe teeming with trillions of other galaxies had ever existed. The evidence of the Big Bang, of cosmic expansion, will have been erased by the very expansion it created. This is perhaps the ultimate way the light year breaks our brains. It forces us to confront not just immense space and time, but the fragility of knowledge itself. It shows us a universe that is actively hiding its own history from us. It presents us with a portrait of cosmic solitude that will only deepen as the eons pass. So, the next time you look up at the stars, remember what you are truly seeing. You are not seeing points of light in a static void. You are seeing distance and time made visible. You are seeing the ghost of a star that is 400 years in the past, next to the phantom of a galaxy that is 2.5 million years in the past, next to the spectre of a quasar that is billions of years in the past. The light year is more than a unit of measurement. It is a philosophical statement. It is a measure of our own insignificance and a testament to the boundless ambition of the human mind. We are ephemeral creatures on a speck of rock, our lives a mere flicker in the cosmic timescale. And yet, from our tiny, isolated vantage point, we have reached out across the void. We have decoded the messages in ancient light. We have built a ladder of logic into the sky. We have measured the beginning and are beginning to glimpse the end. The light year does break our brains. It shatters our comfortable assumptions and exposes our limitations. But in the breaking, there is a profound rebuilding. It replaces our intuition with wonder. It replaces our certainty with humility, and it fills the silent, star-filled night with the deepest and most beautiful story of all, the story of everything, told across an ocean of time. In a universe ablaze with 1 trillion galaxies, each one a celestial empire of fire and dust, how could something the size of our own Milky Way simply hide? How could a structure spanning hundreds of thousands of light years, a titan by any measure, exist as little more than a whisper in the cosmic dark, evading our notice for almost all of human history? This is not a riddle, but a revolution. It is a mystery that begins not in the unknown, but in the heart of what we thought we knew so well. For generations we have gazed out into the deep, charting the grand architecture of the cosmos, and we believed we'd completed the census. We catalogued the great spirals, luminous pinwheels of breathtaking beauty. You know them. You have seen their portraits. Galaxies like Andromeda, our nearest major neighbour, a sprawling disk of such impossible scale that its light has travelled for 2.5 million years to reach your eyes. Its arms are vibrant rivers of stellar birth, glowing with the furious blue light of young massive stars and threaded with dark lanes of interstellar dust, the raw material for future suns. They are dynamic, violent and magnificent, the bustling metropolises of the universe. They are governed by immense central black holes, gravitational anchors around which trillions of tons of matter perform a celestial dance that can last for eons. We measured their spin, we mapped their stars, and we felt a sense of comfortable understanding. Then there were the ellipticals, the ancient kings of the cosmos. These are galaxies that have lived their lives vast round, golden glows of old red stars. They are cosmic cities in retirement, often found at the heart of colossal galaxy clusters, having grown to their monstrous size by relentlessly consuming their smaller neighbours. Look into the heart of the Virgo cluster, and you will find Messier 87, a galaxy not of elegant arms, but of sheer overwhelming presence. It is a gravitational behemoth, a static-filled sphere of 1 trillion suns, whose placid exterior belies the supermassive black hole at its core, a monster. We have photographed a creature that spews jets of plasma across intergalactic space. These were the elder statesmen, the galactic patriarchs, their stories written in the slow ruddy light of their aging stellar populations. And of course we found the irregulars, the wild ones. The Magellanic Clouds, visible to the naked eye in the southern hemisphere, are our most famous examples. They are beautiful chaotic splashes of light galaxies without the discipline of a spiral or the settled nature of an elliptical. They are the rebels, their shapes moulded and torn by the gravitational whims of larger companions, their star formation occurring in frantic, unpredictable bursts. They were the outliers that proved the rule, the exceptions that defined the elegant order of the grand spirals and majestic ellipticals. We had our categories, our labels, our beautiful Hubble mosaics. We had constructed a family album of the universe, and we were proud of its completeness. We stood on our small blue world looking out at this cosmic diorama of spirals, ellipticals and irregulars, and we felt we had a handle on things. We believed we knew what a galaxy was. But the universe, it seems, does not care for our confidence. It delights in ambiguity and subtlety, in hiding its greatest secrets, not in the fire, but in the smoke. To find the next chapter in this story, you have to turn your gaze away from the bright city centres of the cosmos. You must look past the galactic cores, beyond the shimmering disks, and into the enormous, terrifyingly dark spaces in between. You must venture into the intergalactic void, an abyss so profound that the light from the nearest galaxy can take millions of years to cross it. For decades, this was considered the hinterland, a realm of almost perfect nothingness, punctuated only by the occasional stray star flung out from its home. We built new eyes to peer into this darkness, not with the expectation of finding new empires, but to search for the faintest of breadcrumbs, the tidal streams of disrupted dwarf galaxies, the last vestiges of ancient cosmic mergers. One such eye is the Dragonfly telephoto array. It is not a single giant mirror like Hubble, but a hive-like collection of lenses brilliantly designed to detect incredibly faint spread-out light. It is an instrument built to see ghosts. Its purpose was to map the ethereal halos of galaxies, the faint shells of stars that surround the brighter cores. But as astronomers Peter van Dokkum and Roberto Abraham pointed their revolutionary telescope at the Coma cluster, a dense swarm of galaxies 300 million light-years away, they began to see things that shouldn't be there. At first, they were dismissed. Smudges on the lens, atmospheric interference, a glitch in the software. In the raw data, they appeared as faint, almost imperceptible patches of light so diffuse and unassuming that any automated survey would have classified them as meaningless noise and discarded them. But the smudges persisted. Night after night, as the data accumulated, these ghostly apparitions refused to vanish. They were real, and they were enormous. Slowly, painstakingly, the team processed the images, filtering out the glare from bright stars and the noise from the sensors, and an impossible picture began to emerge from the blackness. They were seeing galaxies, but they were galaxies unlike any we had ever conceived. They were vast, spanning the same dizzying distances as our own Milky Way, yet they shone with only a tiny fraction of its light. Imagine a ghostly blueprint of a city, a phantom metropolis as large as New York, but containing only the population of a small town, its few inhabitants scattered miles apart, their lights barely piercing the gloom. This is what they saw. They had a name for them, a name that perfectly captures their enigmatic nature: ultra-diffuse galaxies. The discovery sent a shockwave through the astronomical community. It was as if biologists, having meticulously catalogued all the great animals of the world, the whales, the elephants, the lions, suddenly discovered a new creature. An animal the size of a blue whale, but with the mass of a hummingbird, an entity that defied the known laws of physiology. How could such a thing even exist? The very structure of an ultra-diffuse galaxy, or UDG, is a profound paradox. A galaxy like our Milky Way is a tightly bound system. Its 100 billion stars are held in a powerful gravitational embrace, a cosmic gyroscope that has remained stable for billions of years. This gravitational glue, composed of both the stars themselves and a vast halo of invisible dark matter, allows it to withstand the tidal forces exerted by neighbouring galaxies. But a UDG has no such density. With its stars spread so thinly, the internal gravity should be astonishingly weak. A UDG floating near a massive galaxy like those in the Coma cluster should be treated like cosmic cotton candy in a hurricane. It should be stretched, shredded, and violently torn apart, its few stars scattered into the intergalactic void within a few 100 million years. Yet here they were, not just one, but dozens of them, drifting serenely through one of the most hostile and gravitationally violent environments in the universe. They were ancient, their stars old and red, meaning they had somehow survived in this state not for millions, but for billions of years. They are the ghosts of the universe haunting the very places they should least be able to exist. Take the now famous example of Dragonfly 44, one of the first and most studied of these phantoms. It is a celestial ghost story written in the sky. In deep images, it appears as a barely visible spherical haze, a mere puff of light against the absolute black. But when you measure its distance and calculate its size, you are confronted with a staggering reality. Dragonfly 44 is nearly as large as the Milky Way, yet it emits only 1% of the light. It is a galaxy composed almost entirely of absence. It is a shadow structure, a gravitational afterthought that somehow persists. Its existence is a direct and profound challenge to our most fundamental theories of how galaxies form and evolve. Our models, our sophisticated computer simulations that have been so successful at recreating the grand spirals and giant ellipticals, simply fail when confronted with these spectres. They cannot build them, and they cannot explain their survival. This is where the detective story truly begins. We are the investigators, and these galaxies are the mystery. The crime scene is the entire cosmos, and the clues are photons of light that have travelled for hundreds of millions of years, carrying with them a story we're only now learning how to read. The central question: is this what is holding them together? If the gravity of their visible stars is far too weak to ensure their survival, then some other unseen force, some invisible substance, must be providing the necessary gravitational anchor. The immediate suspect, of course, is dark matter, that enigmatic invisible scaffolding that we believe makes up over 80% of all matter in the universe. For decades, we have inferred its existence by the way it sculpts and corrals the galaxies we can see. So the first hypothesis was simple, almost elegant. Perhaps UDGs are just galaxies that are absolutely saturated with dark matter. Perhaps they are little more than the enormous puffy clouds of dark matter, with just a light sprinkling of stars trapped within them like fireflies in a vast invisible jar. In this scenario, a galaxy like Dragonfly 44 would not be a ghost at all. It would be a monster in disguise. While appearing faint and insubstantial, it would in fact be as massive as the Milky Way, its true heft, hidden in the dark matter realm. This would make it a failed galaxy, a cosmic structure that gathered a normal galaxy's worth of dark matter, but for some unknown reason failed to ignite the brilliant fires of star formation that would have made it a luminous spiral. It would be a relic from the early universe, a glimpse into a pathway of galaxy formation that is far more common than we ever imagined. But the universe is rarely so simple. Just as this intriguing idea began to take hold, a new, even more baffling discovery was made. Another team of astronomers studying another UDG named NGC 1052 DF2 measured the speeds of the star clusters within it. By measuring how fast these clusters orbit, you can weigh the galaxy, determining its total mass, both the visible and the dark. The expectation was that they would find a colossal amount of dark matter holding this fragile system together. What they found was stunning. The star clusters were moving so slowly, so lazily, that they could be entirely explained by the gravity of the stars alone. There was no room for dark matter, none at all. It was a galaxy seemingly without a skeleton, a structure held together by nothing more than its own feeble, visible light. This discovery was met with disbelief then, with intense debate. It broke everything. If UDGs could be packed with dark matter and also be completely devoid of it, then they were not a single coherent class of objects. They were something else entirely, a cosmic puzzle box containing multiple contradictory secrets. How can one galaxy be 99% dark matter, while another which looks almost identical has none? Where did the dark matter go, or did it never have any to begin with? These questions strike at the very heart of cosmology. Dark matter is not just an add-on to our theories, it is the fundamental pillar upon which our entire understanding of cosmic structure is built. Galaxies that can apparently choose to exist with or without it are not just oddities, they are profound anomalies that suggest our pillar may have cracks. We are at the dawn of a new cosmic cartography. For centuries we mapped the brilliant continents of light. Now we must learn to map the shadows. These ultra-diffuse galaxies are forcing us to reconsider our place in the universe, to accept that the cosmos is far more subtle, more diverse and more mysterious than our grandest theories had ever allowed. They are a lesson in cosmic humility. They are proof that even in an age of precision cosmology and breathtaking discovery, there are still ghosts in the machine phantoms in the dark that hold the keys to a deeper understanding of reality. They challenge our definitions, they defy our models, and they beckon us forward into a new realm of inquiry. The hunt is on. To begin to unravel this enigma, we must journey into the most violent and crowded places in the universe, the great galaxy clusters. It is here in these cosmic crucibles, where thousands of galaxies are locked in a chaotic gravitational dance, that the first clues to the origin and survival of these phantoms were found. This is a story of persecution, of resilience, and of an impossible existence played out on the grandest of all possible stages. We must enter the fray, for it is only by understanding the brutal lives of these ghosts that we can ever hope to understand the true nature of the cosmos they haunt. What happens when the universe presents you with a ghost? Not a spectre of folklore, but an object of immense, impossible scale. An entity so vast it rivals our own Milky Way, yet so faint, so utterly ethereal it remained hidden from our most powerful instruments for over a century of looking. It's a question that strikes at the very heart of what we believe we know, challenging the comfortable order we've imposed upon the cosmos. For generations, our map of the heavens was a place of reassuring structure. Galaxies, those grand islands of stars, were thought to fall into distinct families. There were the magnificent pinwheeling spirals, their arms swirling with gas and dust, blazing with the birth of new suns, vibrant and dynamic cities of light. Beside them sat the majestic ellipticals, great serene globes of ancient stars, cosmic megalopolises that had long since settled into a quiet, luminous old age. And of course the irregulars, the wild outliers misshapen by cosmic collisions, chaotic, but still dense, still brilliant, their stories etched in their tangled forms. This galactic census, beautifully captured in Edwin Hubble's famous tuning fork diagram, was more than just a classification scheme. It was a pillar of modern astronomy. It told a story of galactic life, of evolution, of order emerging from chaos. It implied a set of fundamental rules governing how galaxies are built. A core principle seemingly written into the fabric of space-time itself was the simple, intuitive relationship between a galaxy's size and its brilliance. If you were big, you were bright. More mass meant more stars. More stars meant more light, a blazing bonfire in the cosmic dark. A galaxy as expansive as our own with hundreds of billions of suns should be a beacon impossible to miss, a shining landmark on the celestial map. This wasn't just an assumption. It was the bedrock of galactic observation, a foundational truth confirmed by every telescope that had ever stared into the deep. The universe, it seemed, had shown us its hand. We knew the players, we understood the game, but the universe is under no obligation to conform to our expectations. It holds its secrets, closely revealing them only when we build the right key. In the early years of the 21st century, two astronomers, Peter van Dokkum and Roberto Abraham, found themselves wrestling with a problem that was both frustrating and profound. They were hunting for the faintest, most delicate structures in the cosmos, the ghostly trails of stars ripped from galaxies known as stellar streams. These are the cosmic breadcrumbs left behind by ancient gravitational battles, wisps of light so fragile they are utterly swamped by the glare of brighter objects. Imagine trying to spot a single candle flame in the blinding light of a searchlight. That was the scale of their challenge. The sky itself, even on the darkest nights, is not truly dark. It's filled with a faint, pervasive glow, scattered light from countless sources. Worse, within great clusters of galaxies like the nearby Coma cluster, there exists a maddening fog of intra-cluster light. This is the combined ghostly luminescence of billions of orphaned stars' suns torn from their homes and cast adrift to wander the space between galaxies. To conventional telescopes, this fog is an impenetrable wall of noise. Trying to see through it to the even fainter structures within was impossible. It was like trying to hear a whisper in the middle of a roaring stadium. Van Dokkum and Abraham knew that to see these ghosts they couldn't just build a bigger telescope. Bigger mirrors collect more light, but they also collect more of that confounding unwanted glare. They needed something smarter, a new kind of eye designed with surgical precision. They needed an instrument that could see not just deeply, but cleanly. Their solution was an act of radical, almost counterintuitive genius. Instead of one giant expensive mirror, they imagined an array of smaller, perfect lenses. They turned to the consumer market, to the exquisite optical engineering of telephoto lenses, the kind used by professional photographers to capture a bird in flight. Each lens was a masterpiece of optical design coated with nano-fabricated materials that were extraordinarily effective at suppressing scattered light and internal reflections. By linking dozens of these lenses together, they could create a compound eye, a digital beast that would stare at the same patch of sky for hours, even days. This was the birth of the Dragonfly telephoto array. It looked less like a traditional observatory and more like a strange futuristic weapon, a honeycomb of high-tech glass aimed at the heavens. Each lens was a separate pristine channel, and by combining their data, the team could digitally subtract the glare, the noise, the fog. They could effectively peel back the layers of contaminating light, revealing the pristine, impossibly faint universe hiding beneath. Their primary target was the Coma cluster, a sprawling metropolis of galaxies over 300 million light-years away, a known graveyard of cosmic collisions. It was the perfect hunting ground for the stellar streams they sought. The Dragonfly array began its long, patient vigil, its electronic shutters opening its sensors, drinking in the ancient light from this distant city of galaxies. The data began to accumulate terabytes of information flowing into their computers. As they processed the initial images, painstakingly removing the light from bright stars, subtracting the glow from massive foreground galaxies, the fog began to lift. And in the silent darkness of their digital workspace, something began to emerge. It wasn't the thin, looping tendrils of a stellar stream they had expected. At first, it was just a smudge, a faint, barely perceptible patch of light, the kind of thing most astronomers would dismiss as an artifact, a camera glitch, a reflection in the optics, or simply a patch of uncorrected background noise. It was nothing. It had to be nothing. But then as they refined the data from another part of the cluster, there was another one, and another, and another. These smudges were persistent. They appeared in multiple observations. They survived every diagnostic test the team could throw at them. This wasn't an error. It was real. A quiet sense of confusion mixed with a thrilling current of discovery began to ripple through the research team. What were they looking at? These objects were incredibly faint, possessing a surface brightness so low they were barely distinguishable from the background sky itself. They were almost entirely transparent. You could see distant galaxies right through them, as if they were nothing more than a thin veil of smoke against the cosmic black. The initial logical assumption was that they must be small and nearby. Perhaps they were a new type of dwarf galaxy, little puffs of stars drifting in the foreground close to our own Milky Way. That would make sense. Small things are often faint, but to know for sure they needed to know their distance. Determining cosmic distances is one of the most challenging tasks in astronomy. For these phantom objects without bright, obvious stars to serve as landmarks, it seemed an almost insurmountable problem. The team had to use a different method analysing the faint collective shimmer of the object's entire stellar population to see if it was part of the Coma cluster. They pointed larger, more traditional telescopes like the Keck Observatory in Hawaii at the precise coordinates Dragonfly had identified. They were effectively aiming one of the world's most powerful instruments at a patch of sky that to its own electronic eyes appeared almost completely empty. They had to collect photons for an agonizingly long time, letting the faint light build up one particle at a time until a coherent signal could be teased from the noise. The results when they finally came were staggering. Utterly paradigm-shattering. The light from these smudges was redshifted by an amount that placed them unequivocally deep within the Coma cluster, 300 million light-years away. They were not small, nearby puffs of stars. They were true citizens of that distant galactic metropolis, and once you know the distance to an object, you can calculate its true size. The team ran the numbers again and again, unable to trust what they were seeing. The calculations were unforgiving. The conclusion was inescapable. These ghostly smudges, these barely there apparitions, were enormous. Some were as physically large as our own Milky Way galaxy, a galaxy spanning 100,000 light-years from edge to edge, yet containing only 1% of the stars. Let that sink in. Imagine a city the size of London, sprawling for miles in every direction, but with the population of a small village. Its streets would be empty, its buildings dark. From a distance at night it would barely register as a glow. You would fly over it and see almost nothing but darkness. This is what they had found. Galactic skeletons. Structures with the size and scale of a majestic spiral, but stripped of nearly all their substance, leaving behind only a faint spectral outline. They were ghosts haunting the cosmic graveyard of the Coma cluster. The discovery sent shockwaves through the astronomical community. These objects, which the team christened ultra-diffuse galaxies or UDGs, simply should not exist according to the prevailing models of galaxy formation. Our theories told us that for a galaxy to grow so large, it needed a colossal gravitational anchor at its core. This anchor of vast halo of invisible dark matter is the seed of a galaxy. Its immense gravity is what pulls in gas from the cosmic web, igniting the furious starbirth that fills the galaxy with light and life. A galaxy as large as the Milky Way should have a correspondingly massive dark matter halo, and it should have experienced a rich, violent history of star formation. It should be blazing with the light of hundreds of billions of stars. But these UDGs were vast and empty. Where were all their stars? How could something grow to such a colossal size without ever truly coming to life? It was as if the universe had built a grand celestial cathedral, laid the foundation, erected the towering walls and soaring arches, but then simply failed to install any lights, leaving it a cavernous dark echo. The very first UDG identified, named Dragonfly 44, became the poster child for this enigma. It was a monster comparable in size to our own galaxy, a shadowy titan lurking in the heart of the Coma Cluster. Yet it was 1,000 times dimmer than the Milky Way. Its few scattered stars were spread out so thinly across its immense volume that if you were standing on a planet within it, the night sky would be profoundly empty. You might see only a handful of lonely stars, the galactic core a barely visible smudge. You would feel an overwhelming sense of isolation adrift in an almost starless void, yet know you were inside one of the largest structures in the universe. This paradox was the central maddening mystery. These objects were not just a new classification. They were a fundamental challenge to our understanding of the universe. They were cosmic questions rendered in faint scattered starlight. Were they failed galaxies, cosmic stillbirths that never managed to ignite? Or were they the exhausted remnants of once mighty galaxies, their stars and gas brutally stripped away by the violent environment of the cluster, leaving behind only a bloated skeletal wreck? Could they even hold themselves together? A collection of stars this diffuse should be easily torn apart by the powerful gravitational tides of its more massive neighbours. For them to survive at all suggested they must possess an unseen strength, a gravitational glue far more powerful than their visible matter would imply. This hinted at the second, even deeper layer of the puzzle, a mystery that would lead astronomers down a rabbit hole of dark matter, questioning the very nature of this invisible substance that holds the cosmos together. The discovery of ultra-diffuse galaxies was a profound lesson in cosmic humility. It proved that even in well-studied familiar corners of the sky, astounding secrets can lie hidden in plain sight, waiting for a new way of seeing. It showed us that the universe is always more strange, more complex and more beautiful than we can imagine. They were the first whispers of a new cosmic narrative, a story that was about to unfold, challenging everything we thought we knew about the birth, life and death of galaxies. The hunt was on. Now that astronomers knew what to look for, they began to see these phantoms everywhere. They looked not just in Coma, but in other galaxy clusters across the universe. A whole new class of celestial object had been unveiled, but finding them was only the beginning. The real work was just starting the struggle to understand what they are, where they came from, and what they can tell us about the hidden architecture of the cosmos. For in the faint, fragile light of these galactic ghosts, we might just find the key to unlocking the deepest secrets of the darkness itself. So the ghosts were there lurking in the intergalactic dark. But to see a phantom is not to understand it. How do you weigh a whisper? How do you chart the anatomy of a shadow? These galaxies, so faint they were functionally indistinguishable from the background noise of the cosmos, presented a challenge that bordered on the impossible. Our grandest telescopes, marvels of engineering designed to capture the first light of creation, were built to see things that were bright or distant or both. Their giant monolithic mirrors gather photons with brute force, like casting a vast net into the cosmic ocean. But ultra-diffuse galaxies are not distant lighthouses. They are a subtle mist spread so thinly across the water that the net passes right through. The light from a UDG is so tenuous, its surface brightness so low, that it is easily lost in the glare of our own atmosphere, the faint glow of our solar system's dust, and the scattered light from within the telescope itself. It's an exercise in supreme frustration, like trying to hear a pin drop in the middle of a thunderstorm. The signal you're hunting for is buried, drowned beneath 100 layers of noise. A new kind of eye was needed, not necessarily a bigger one, but a cleverer one. One designed specifically to see the unseen, to perceive the incredibly subtle gradients of light that betray the presence of these galactic ghosts. The solution, when it came, was elegant, counterintuitive, and born from humble technology. Instead of one colossal lens, astronomers built an array of smaller ones, telephoto lenses, in fact the kind a nature photographer might use. This instrument, aptly named the Dragonfly Telephoto Array, was a masterpiece of lateral thinking. Each lens was coated with revolutionary nanofabrics that minimized scattered light, the very contamination that had blinded other telescopes to these phantoms. By linking dozens of these lenses together, They could create a single wide-field view of the sky with unparalleled clarity specifically tuned to detect low surface brightness. But even with this specialized hardware, a single exposure, no matter how long, would not suffice. The universe is a messy place. A long exposure photograph is a canvas upon which cosmic rays strike like random paint splatters. Satellites streak across the frame like careless brushstrokes. The Earth's own atmosphere shimmers and distorts, blurring the masterpiece. The real breakthrough was not just in the hardware, but in the philosophy of observation. To see the ghost, you couldn't just stare at it. You had to build it piece by piece from 1,000 fleeting glimpses. The technique is called image stacking, but the name belies the sheer artistic and computational brute force it requires. Imagine taking not one, but thousands of relatively short exposures of the same patch of sky. Each individual frame is almost useless and noisy, chaotic mess where the UDG is completely invisible. But within that chaos, the ghost is always there, a persistent faint signal in the exact same place. The noise, however, the satellite trails the cosmic ray hits is random. It's in a different place every time. Now begins the work of digital archaeology. Powerful algorithms sift through this mountain of data, this digital cacophony, with a singular purpose. They align every single image with microscopic precision, layering them one on top of the other like translucent vellum. The software then performs a statistical miracle. It looks at every single pixel in the stack and calculates the average value. For any given pixel, a random satellite trail might appear in a few frames, a cosmic ray in a dozen more. But when you average thousands of frames together, these random events are diluted into statistical insignificance. They simply fade away. The light from the galaxy, however, the one constant in every single frame, gets stronger and stronger. The signal is reinforced, the noise is cancelled out. Slowly, painstakingly, an image begins to emerge from the static. It is an act of creation of weaving light from 1,000 threads of data. Out of the blackness, a fragile, sprawling structure resolves itself, impossibly large and heartbreakingly faint. What was once invisible noise becomes a coherent entity, a galaxy revealed not by a single heroic observation, but by the patient collective power of thousands. We were no longer just looking at the sky. We were computationally excavating it, brushing away the dust of instrumental error and cosmic chance to reveal the fossilized light of a forgotten city of stars. And once we could finally see them clearly, these ghosts began to speak. Their first words were riddles that struck at the very heart of what we thought we knew about how galaxies are made. The first profound shock came not from the diffuse sea of stars, but from tiny, intensely bright pinpricks of light embedded within it. From a distance, they looked like foreground stars from our own Milky Way, a simple case of cosmic coincidence. But as we looked closer, analysing their colour and their motion, a stunning truth was revealed. These were not local stars at all. They were globular clusters, ancient dense swarms of hundreds of thousands of stars, all born together in a single burst of creation, more than 10 billion years ago. Globular clusters are the elder statesmen of the universe. They are gravitational relics, cosmic fossils that orbit large galaxies like loyal satellites, survivors from an epoch when the cosmos was young and violent. And here was the first screaming paradox. The number of globular clusters a galaxy possesses is thought to scale with its total mass. Our own Milky Way, a grand spiral, has about 150 of these ancient systems in its gravitational thrall. A small dwarf galaxy with 1,000 times fewer stars might have a dozen or perhaps none at all. It was a clear established relationship. Yet when astronomers counted the globular clusters around a UDG in the coma cluster known as Dragonfly 44, they found something that should have been impossible. This ghostly galaxy, which contained only 1% of the stars of the Milky Way, was surrounded by nearly 100 globular clusters. It was like finding a tiny fishing village with a population of a few hundred people that somehow supported a fleet of 100 aircraft carriers. The numbers simply did not add up. The discovery sent ripples of confusion and excitement through the astronomical community. What could it possibly mean a galaxy's worth of stars had seemingly vanished, but its ancient entourage of globular clusters remained behind? This wasn't a normal dwarf galaxy that had simply failed to grow. This was something else entirely. It was the stellar equivalent of a ghost ship. All the lifeboats were still there, but the crew and passengers had disappeared. The evidence pointed towards a dramatic and violent past. Perhaps theorists proposed Dragonfly 44 wasn't a dwarf galaxy at all. Perhaps it was a failed Milky Way. It may have started its life as a colossal seed of gas and dark matter on track to become a majestic spiral just like our own. It would have formed its rich system of globular clusters in a magnificent flurry of starbirth at the dawn of time. But then something went terribly wrong. For this nascent galaxy, its birthplace in the dense hostile environment of the Coma cluster was a death sentence. As it plunged through the superheated gas that fills the space between the cluster's larger galaxies, a process called ram pressure stripping acted like a celestial blowtorch, blasting away all of its fuel for making new stars. Its growth was violently prematurely arrested. Star formation shut down. Over billions of years, what could have been a brilliant spiral was left as a pale imitation of itself, a vast diffuse skeleton of its former potential, populated only by its oldest, most resilient stars and the stubborn gravitational anchors of its globular clusters. The galaxy's stars had been scattered, its substance diluted, but its history was written in these surviving stellar jewels. It was a compelling, even romantic narrative, the story of arrested development on a cosmic scale. But as we turned our new eyes to other UDGs, the ghosts revealed a second, far more profound and deeply heretical secret. The globular cluster puzzle, as strange as it was, could at least be tentatively explained within our existing models. The next discovery could not. It threatened to pull a foundational thread from the entire tapestry of modern cosmology. That thread was dark matter. For decades, we have understood that the universe we see is only a tiny fraction of what is actually there. The stars, the gas, the dust, all the normal matter, is just the glittering froth on a deep invisible ocean of dark matter. This mysterious substance, which we cannot see or touch, provides the immense gravitational scaffolding upon which all cosmic structures are built. Without it, galaxies would fly apart. Without its gravitational pull in the early universe, gas would never have collapsed to form galaxies in the first place. The rule was simple and absolute. Where you find a galaxy, you find a massive halo of dark matter surrounding it. In fact, for a typical galaxy, dark matter outweighs normal matter by a factor of 5-10, or in some extreme cases, even 100 to 1. Measuring that invisible mass requires a cosmic sleight of hand. We can't see the dark matter itself, but we can see its influence. By tracking the orbits of visible objects like those very same globular clusters, we can effectively weigh the entire galaxy. Just as the Sun's gravity dictates the speed of the Earth's orbit, the total mass of a galaxy, both visible and dark, dictates the speed of its globular clusters. The faster they move, the more mass there must be pulling on them with its relentless gravity. So astronomers pointed their most powerful spectrographs at the UDGs. They painstakingly measured the subtle Doppler shift in the light from their globulars, calculating their orbital velocities with breathtaking precision. For Dragonfly 44, the results were astonishing, but in a way expected. The clusters were moving incredibly fast. So fast, in fact, that the gravity from the visible stars couldn't possibly hold on to them. To explain their speed, the galaxy had to be almost entirely made of dark matter. The final calculation was a mind-bending 99.9% dark matter. Dragonfly 44 was less a galaxy of stars and more a gargantuan galaxy-sized clump of dark matter that just happened to have a light dusting of stars within it. This was an extreme case, but it still fit the paradigm. The fundamental rule held. A galaxy is a nugget of normal matter embedded in a vast sea of dark matter. But then they turned their attention to another UDG, a faint smear in the constellation Cetus named NGC 1052 DF2. They performed the same meticulous measurements tracking its small family of globular clusters. They ran the calculations, and they stared at their screens in disbelief. They ran them again. The results didn't change. The globular clusters in DF2 were moving slowly. Shockingly slowly. Their velocities were so low they could be explained entirely by the gravitational pull of the stars alone. There was no need for dark matter. There was no room for dark matter. The galaxy, as far as our instruments could tell, was made only of what we could see. This was not supposed to happen. Ever. It was like discovering a human being who was alive and walking but possessed no skeleton. It was a violation of the most basic tenets of galaxy formation. How could this object even exist? The standard model of cosmology known as lambda CDM is unequivocal on this point. Galaxy formation begins with a dark matter halo. Its immense gravity acts as a cosmic seed pulling in pristine hydrogen and helium gas from the void. That gas then cools, collapses, and ignites into stars. The dark matter comes first. It is the prerequisite, the non-negotiable ingredient for building a galaxy. Yet here was NGC 1052 DF2, and later its cousin DF4 apparently formed without any. It was a cosmological crisis in the form of a faint, unassuming smudge of light. It suggested that either our fundamental understanding of how galaxies form was catastrophically wrong, or that some unknown exotic process could somehow separate a galaxy from its dark matter, anchor a feat with no known mechanism in physics. The ghosts of the universe had presented us with two seemingly irreconcilable realities. On one hand, there were UDGs like Dragonfly 44 overflowing with both dark matter and the globular cluster relics of a once grand history, pointing to a life of thwarted ambition. On the other, there were impossible phantoms like DF2, seemingly devoid of the one ingredient considered essential for existence, yet somehow holding themselves together in the void. These were not mere oddities anymore, not fringe curiosities to be filed away in a catalogue of cosmic strangeness. They had become direct, profound challenges to the grand narrative of cosmic evolution we had spent a century building. They were cosmic interrogators, forcing us to question the very foundations of our theories. How can some ghosts be so heavy and others so light? How can one galaxy be a failed giant and another a cosmic impossibility? The scientific community was split and the debate became fierce. The search for answers would lead astronomers down two warring paths of explanation, each with the power to completely rewrite our understanding of the dark, invisible universe. And so the paradox was laid bare before us. These phantoms, vast and empty, drifted through the cosmic dark, challenging everything we thought we knew about how a galaxy is made. They were an affront to our models, a whisper of a cosmic rulebook we had never read. The shock of their discovery, which we've now seen ripple through observatories across the globe, quickly gave way to a deeper, more urgent question. It's a question that follows any profound anomaly in science and in life. Not just, what are you, but how did you come to be in the quiet halls of astrophysics where data and theory collide? The silence was broken by the sound of a community dividing. The puzzle of the ultra-diffuse galaxies would not yield a single simple answer. Instead, it ignited one of the most compelling scientific debates of the modern astronomical era, splitting researchers into two distinct, fiercely defended camps, each armed with compelling evidence and a powerful narrative. It was a schism that centered on a timeless question. Are we shaped by the brutality of our environment, or by the unalterable nature of our birth? The first great theory to emerge was one of violence and transformation. Its proponents looked at where many of these early spectres were found, haunting the gravitational cores of massive galaxy clusters, like the Coma or Virgo clusters. To them, the location was not a coincidence. It was the entire story. They saw the UDGs not as born ghosts, but as the tortured remnants of something that was once normal. This is the puffed-up dwarf hypothesis, a dramatic tale of survival against impossible odds. To understand it, you must first picture the environment it requires. A galaxy cluster is not a serene starscape. It is a metropolis of cosmic cannibals, a gravitational crucible where thousands of galaxies are locked in a chaotic multi-billion-year dance of death and consumption. The space between them is not empty, but filled with a searingly hot, thin gas, a ghostly fog superheated to millions of degrees. Through this maelstrom, smaller galaxies, ordinary dwarf galaxies, plunge like moths into a flame. According to this model, a small compact dwarf galaxy teeming with stars and rich in star-forming gas begins its fall into the cluster's unforgiving heart. For this unfortunate galaxy, the journey inward is a gauntlet of escalating torment. First, it encounters the ram pressure of that superheated intracluster medium. The galaxy is moving at thousands of kilometers per second, and this intergalactic gas, thin as it may be, acts like a cosmic sandblaster scouring the dwarf of its own precious cold gas, the very fuel for future generations of stars. Its lifeline is severed. Star formation grinds to a halt, a process astronomers call quenching. The galaxy is now sterile, its brilliant blue stellar nurseries extinguished, leaving only the fading embers of its older, redder stars. It is the first step toward becoming a ghost, but the true transformation, the dramatic inflation, is yet to come. This is where the monstrous gravity of the cluster itself takes centre stage. The force at play is not simple attraction, it is the insidious stretching power of tidal forces. Imagine our dwarf galaxy drawing closer to the cluster's core, where colossal elliptical galaxies, cosmic behemoths, weighing trillions of suns, hold court. The gravitational pull on the near side of the dwarf becomes significantly stronger than the pull on its far side. This differential is a relentless cosmic torture rack. It grabs the small galaxy and begins to stretch it to pull it apart like taffy. Stars on the periphery, those held most loosely by the dwarf's own gravity, are the first to be lost. They are ripped away, forming long ghostly streams of stellar confetti that dissipate into the cluster's void, a faint memory of the galaxy they once called home. But here is the crucial counterintuitive twist in the tale. For some galaxies under just the right conditions of mass and trajectory, this tidal harassment doesn't lead to complete annihilation. Instead, the repeated gravitational shocks, the constant pulling and flexing, energize the orbits of the remaining stars. Think of it like repeatedly striking a bell. The energy doesn't just pass through, it resonates, changing the internal state. The stars once held in tight, orderly orbits are kicked into higher, wider, more eccentric paths. They are flung outwards away from their galaxy's core, but not with enough energy to escape entirely. They are now bound in a much larger, more tenuous gravitational embrace. The very architecture of the galaxy is rearranged, its stellar density plummets. It inflates, ballooning to 1050, even 100 times its original size, its few remaining stars now scattered across a volume that rivals a true giant like the Milky Way. It has been puffed up, transformed from a compact living system into a vast diffuse relic. It is now a ghost, a testament to the violence it endured. The initial evidence for this dramatic story was incredibly persuasive. The Dragonfly telephoto array, the very instrument that opened our eyes to this new class of object, found dozens of these UDGs huddled within the coma cluster. It was a collection of suspects found at the scene of the crime. The correlation was too strong to ignore. To the proponents of the tidal stripping model, the case seemed almost closed. These galaxies were victims, their diaphanous nature a scar left by the brutal environment of the cluster. They pointed to simulations, powerful computer models that could fast-forward the universe, showing that when you throw a simulated dwarf galaxy into a simulated cluster, you could, under the right circumstances, produce an object that looked uncannily like a UDG. The theory was elegant, grounded in well-understood physics, and it perfectly explained the UDGs found in the most violent corners of the universe. It was a story of nurture, or rather a lack of it, a story of cosmic bullying on the grandest scale imaginable. The ghosts of the cluster were not a new species of galaxy, but the battered souls of a familiar one. But the universe is rarely so simple. Just as the scientific community began to rally around this compelling narrative of tidal torment, new discoveries began to emerge from the loneliest parts of the cosmos, throwing the entire theory into question. Telescopes now specifically hunting for these phantoms started finding them not in the crowded, violent metropolis of a cluster, but in the cosmic equivalent of the deep countryside, the field. These were ultra-diffuse galaxies living in profound isolation, some with no significant neighbour for millions of light-years in any direction. They were cosmic hermits living a quiet existence far from the gravitational war zones where their cluster-bound cousins were being brutalised. For these isolated ghosts, the puffed-up dwarf story simply could not work. There was no colossal cluster to blame for their condition. There was no gravitational rack to stretch them, no superheated gas to strip them bare. They were alone. This profound observational challenge gave rise to the second great theory, a counter-narrative that was in many ways even more radical. If the environment couldn't be responsible, then the explanation must lie within the galaxies themselves. It must be something fundamental, something imprinted upon them from the moment of their formation. This is the failed giant hypothesis, a theory not of nurture but of nature. It proposes that these galaxies are not victims of circumstance, but are instead born anomalies, the result of a cosmic misfire at the dawn of time. To grasp this idea, we have to journey back to the very blueprint of galaxy formation, to the unseen architecture that underpins the visible universe, the web of dark matter. As we've explored, every galaxy, including our own Milky Way, is thought to reside within a vast invisible halo of this mysterious substance. This halo acts as a gravitational seed, its immense gravity pulling in primordial hydrogen and helium gas from the void. It is this captured gas that cools, collapses and ignites into the billions of stars that make a galaxy shine. The mass of the dark matter halo dictates the ultimate destiny of the galaxy it will host. A modest halo builds a dwarf, a truly massive one like our own builds a spiral giant. The failed giant theory hinges on a subtle but critical property of these dark matter halos. It posits that not all halos of the same mass are created equal. Some, through a quirk of their initial conditions in the early universe, might be born with an unusually high amount of angular momentum or spin. Imagine a spinning figure skater. When they pull their arms in, they spin faster. When they extend their arms, they slow down. A rapidly spinning dark matter halo is like the skater with arms outstretched. It is larger, more diffuse, and its gravitational pull, while still immense overall, is less concentrated at its centre. It is a fluffy halo, a gravitational seed that lacks the necessary density to aggressively build a galaxy. Now picture this enormous, rapidly spinning, low-density dark matter, Halo 1, with enough mass to theoretically form a giant like the Milky Way as it begins its work. It attempts to pull in gas from its surroundings, but its grip is weak and spread out. The gas is captured less efficiently. The gas that is captured finds it much harder to cool and sink to the centre, where star formation is most fervent. The result of this inefficiency is a cosmic tragedy of unfulfilled potential. Over billions of years, the galaxy that forms within this halo is a shadow of what it could have been. It has the immense dark matter skeleton of a giant, granting it a colossal size, but it never accumulates enough gas in one place to fuel a brilliant burst of star formation. Its star-building process is anemic, sputtering along at a pathetically low rate spread out across a vast area. Generations of stars are simply never born. The galaxy fails to populate its enormous home with a fitting number of stars. What you're left with is a ghostly caricature, a system with the size and mass of a giant galaxy, but with only 1% of its stars. A vast dark empire ruled by a tiny scattered population. It is not a dwarf that was puffed up, but a giant that was starved from birth. It is a failed Milky Way. This theory too found powerful supporting evidence. The existence of UDGs in the lonely cosmic void was its primary exhibit. These isolated systems had no other explanation. Their strange nature had to be innate. They must have been born this way. Furthermore, early tentative measurements of the internal dynamics of some of these galaxies began to hint at something extraordinary. By measuring the speeds of their sparse star clusters, astronomers could weigh the galaxies, estimating their total mass, including dark matter. The initial results were staggering. Some of these diaphanous galaxies, like the eponymous Dragonfly 44, appeared to be overwhelmingly dominated by dark matter. They seemed to possess the dark matter mass of a galaxy like our own, just as the failed giant theory predicted. They truly were giants in disguise, their luminous bodies just the tip of a colossal dark matter iceberg. This camp argued that all UDGs were born this way, and those found in clusters were simply the ones that happened to form in or later fall into those dangerous environments. Their puffiness was a birth defect, not an injury, and so the battle lines were drawn. On one side, the environmentalists arguing for a story of transformation of violence and survival, with the cluster UDGs as their prime evidence. On the other, the nativists arguing for a story of arrested development of unfulfilled potential, pointing to the isolated UDGs as their proof. The debate raged at conferences and in the pages of scientific journals. Was it nature or nurture? Each new observation was scrutinized, interpreted by both sides to bolster their own case. An observation of a UDG with a faint tidal stream would be hailed as a victory for the puffed-up dwarf model. The discovery of another perfectly symmetrical, undisturbed UDG in the void would be celebrated as definitive proof of the failed giant scenario. The field was at a critical impasse. The universe, it seemed, was providing evidence for two mutually exclusive realities. It felt as if there were two different kinds of ghost created by two entirely different processes, yet they looked almost identical. This ambiguity was a sign that we were missing a crucial piece of the puzzle. Our understanding was incomplete, our view of these galaxies still frustratingly superficial. We were judging them from the outside by their location and their ghostly appearance. To truly solve the mystery to arbitrate between these two powerful ideas, we would need to look deeper. We needed a way to peer into the very hearts of these phantoms, to dissect their internal structure, to read the history written in the motions of their stars and the ancient relics they held within. A new tool, a new kind of observation was needed to break the stalemate. The universe, it turns out, was about to provide one. A discovery was coming focused on a tiny population of objects orbiting within these galaxies that would not only challenge both prevailing theories, but would plunge the mystery of the ultra-diffuse galaxies into an even deeper, more bewildering realm. The ghosts, it seemed, were guarding a far stranger secret than anyone had ever imagined. And so, the argument echoed through the halls of astronomy. Were these translucent giants primordial failures born anemic and unable to ignite a stellar firestorm, or were they the exhausted relics of once mighty galaxies, their luminous hearts now faded, and their bodies stretched thin by the relentless pull of cosmic tides? The debate itself was a sign of a healthy science, a community pushing at the frontiers of knowledge, wrestling with two compelling but opposing narratives. Each side had its evidence, its models, its champions. But science, in its relentless pursuit of truth, is never content with a stalemate. It demands a deciding vote, a final piece of evidence that can shatter one hypothesis and elevate another. As astronomers at observatories around the world continued their ghostly census, they began to focus on a detail that should have been straightforward, a simple accounting exercise. They were trying to weigh these phantoms. To do this, you don't need a cosmic scale, you need a cosmic speedometer. You find something inside the galaxy that is in orbit, a star, a gas cloud, or in the case of these UDGs, one of their ancient glittering globular clusters. You measure its velocity. The speed of its orbit is a direct report on the total gravitational force holding it in place. It tells you precisely how much mass is inside its orbital path, both the mass you can see and the mass you can't. It is the standard time-tested procedure for weighing a galaxy, the bedrock technique that first revealed the existence of dark matter decades ago. For every galaxy ever measured, from the smallest dwarf to the most majestic spiral, the story was the same. The stars and clusters were moving too fast to be held in place by the visible matter alone. This excess velocity was the irrefutable signature of a massive invisible halo of dark matter, a gravitational scaffold holding everything together. Dark matter wasn't just an addition to a galaxy, it was its very foundation, its skeletal system, its anchor in the cosmos. A galaxy was, in essence, a visible froth of stars and gas collected at the deepest point of a colossal dark matter well. This was not a theory, it was a fundamental observed reality of the universe, until it wasn't. The year is 2018. A team led by astronomer Peter van Dokkum is using the Dragonfly telephoto array, the very instrument designed to hunt for these faint smudges, in concert with the world's most powerful telescopes. They turn their gaze towards a wispy patch of light in the constellation Cetus, a UDG catalogued as NGC 52DF2. It was a ghost like any other, a faint distended haze of stars. Following the standard procedure, they began measuring the velocities of its 10 brightest globular clusters, using them as tracers, as probes of the galaxy's hidden mass. The data began to stream in from the Keck Observatory in Hawaii, each photon carrying a piece of the puzzle from 65 million light-years away. And as the numbers resolved on their screens, a profound and unnerving silence must have fallen over the control room. The numbers were wrong. They were impossibly, fundamentally wrong. The globular clusters were moving, slowly. They were crawling through space at a speed that could be explained entirely by the mass of the stars you could see. There was no excess velocity. There was no gravitational signature of a hidden halo. When they finished the calculations, the conclusion was as stark as it was terrifying. NGC 52DF2 appeared to have no dark matter, none at all. It was a result that simply should not be possible. A building without a foundation, a body without a skeleton, a gravitational ghost stripped of its very essence. The announcement sent an immediate and powerful shockwave through the cosmological community. The reaction was not excitement, but a deep resounding skepticism. The The universe had rules. Lambda CDM, the standard model of cosmology, was the rulebook written from decades of painstaking observation of the cosmic microwave background, of galactic rotation, of the large-scale structure of the universe. And that rulebook stated unequivocally that galaxies form within dark matter halos. The dark matter comes first. It is the seed, the gravitational cradle into which gas falls, cools, and ignites into stars. To find a galaxy without dark matter was not just an anomaly, it was a cosmic heresy. It was like finding a human child that had developed and been born without ever having a biological mother. It violated the established order of creation. So the counter-arguments began swift and logical. The most obvious point of attack was the distance. Measuring the distance to faraway galaxies is notoriously difficult. If the team had gotten the distance to DF2 wrong, the entire result would collapse. If the galaxy were in fact much closer to us than they calculated, then its stars would be intrinsically dimmer, smaller and less massive. Its globular clusters would just be faint star clusters, not the massive beacons they appeared to be. The entire mass budget would change and the need for dark matter might simply evaporate. It was a powerful and elegant critique. The burden of proof was now on the Discovery team to defend their most basic measurement. They returned to the data employing the most reliable yardstick in the cosmos, the light from specific pulsating variable stars within the galaxy itself. These stars are cosmic metronomes, their pulsation period directly linked to their true brightness. By comparing their true brightness to their apparent brightness in our sky, you can calculate their distance with remarkable precision. The result came back, and it was unambiguous. The original distance was correct. DF2 was indeed a resident of the NGC 1052 group 65 million light-years away. The first line of defense for the standard model had crumbled. The skeptics pivoted to a new line of argument. Perhaps the globular clusters themselves were the problem. Maybe the 10 clusters they measured were not representative of the entire population. Perhaps they were on strange plunging orbits that only made them appear to be moving slowly from our line of sight. It was a statistical longshot, a desperate grasp for a conventional explanation. But science requires more than one data point. An anomaly can be dismissed, a pattern cannot. So the team went hunting again, and soon they found another one. In the same galactic group, they identified a second UDG, NGC 1052 DF4, that looked hauntingly similar to its sibling. Once more, they trained the world's great observatories on this new ghost. Once more, they meticulously measured the velocities of its star clusters, and once more the universe delivered the same impossible answer. DF4 also seemed to be missing its dark matter. The anomaly was becoming a population. The exception was threatening to become a new rule. This was no longer a curious outlier that could be swept under the rug. This was a direct observational challenge to the deepest foundations of modern cosmology. For decades, we have built our grand cosmic narrative upon the invisible pillar of dark matter. It is the hero of our story of structure formation. In the primordial universe, the dark matter immune to the pressure of light began to clump together under its own gravity long before normal matter could. It formed vast, sprawling halos, a cosmic web of invisible filaments stretching across the universe. Normal matter, the stuff of stars and planets, and people, was a latecomer to the party. It was pulled by the gravity of these pre-existing dark matter structures falling into the deepest gravitational wells to begin the process of building galaxies. Without the dark matter, halos providing the initial gravitational scaffolding, the gentle density fluctuations in the early universe would never have had enough pull to overcome cosmic expansion and form the galaxies we see today. Under the Lambda CDM model, a galaxy without a dark matter halo is an impossibility, a contradiction in terms, and yet here were two of them. And as other teams began looking, more candidates started to appear elsewhere in the universe. The ghosts were no longer just a curiosity, they were a crisis. Physicists and astronomers, faced with this undeniable observational evidence, were forced into a profound and uncomfortable reckoning. If these objects are real, if they truly lack dark matter, then what could they possibly be? How could they have formed? The frantic search for an explanation began branching into three deeply consequential paths. The first path sought to save the standard model by finding a way to create these galaxies within its existing rules. The most plausible mechanism was violence. Perhaps these galaxies weren't born without dark matter. Perhaps they had it stolen. This is the theory of tidal stripping. Imagine DF2 and DF4 were once normal dark matter-rich dwarf galaxies, orbiting their massive neighbour, the giant elliptical galaxy NGC 10^52. Over billions of years, with each close pass, the immense gravity of the larger galaxy would have acted like a cosmic tide. This tide would pull and stretch the smaller galaxies. The dark matter forming a vast diffuse halo is less tightly bound than the stars concentrated at the centre. So with each pass, the bigger galaxy could have peeled away layers of the dark matter halo, flinging them into intergalactic space. Eventually, after countless orbits, all that would be left behind is the naked star-filled core, a galaxy stripped of its invisible majority, a refugee of a gravitational war. It is a compelling, elegant idea. It explains not just the lack of dark matter, but also why these objects are so diffuse and distended, their shapes warped by the very forces that dismembered them. But when astronomers looked for the evidence, the story grew complicated. There were no obvious tidal tails, no streams of stars stretching away from DF2 or DF4, the telltale scars of such a violent encounter. And their globular cluster system seemed strangely intact, not disrupted as one might expect. The crime scene lacked the evidence of a struggle. The second path was more exotic, but still operated within the realm of known physics. It invokes one of the most dramatic events in the universe, a galactic collision. We have seen in places like the famous Bullet Cluster what happens when two galaxy clusters collide at incredible speeds. The stars and dark matter, being essentially collisionless, pass through each other like ghosts, but the vast clouds of interstellar gas in each cluster slam into each other, creating a shock wave of unimaginable power and heat that slows the gas down. The result is a spectacular separation. The dark matter and stars continue moving in one direction, while the hot gas is left lagging behind. Could DF2 and DF4 be a strange galactic-scale version of this process? Perhaps a high-speed collision or interaction in their past somehow separated their normal matter from their dark matter halo. They could be the baryonic shrapnel from a cosmic impact, a cloud of stars and gas that was ejected and sent tumbling through space, leaving its dark matter parent behind. This scenario, while intriguing, requires a very specific and perhaps unlikely chain of events. It posits that these galaxies are not a normal class of object, but the exceedingly rare debris from a celestial cataclysm. As more and more of these dark matter deficient candidates are found, the likelihood of each one being the result of a rare accident diminishes. The crisis was deepening. The conventional explanations, while clever, seemed to be struggling to fit the growing body of evidence. And so cosmologists were forced to walk down the third most treacherous path. The path that questions not the history of the galaxies but the fundamental rules themselves. What if the problem isn't with the galaxies but with our understanding of dark matter, or even more radically, with our understanding of gravity? This is where the ghost galaxies cease to be mere astronomical curiosities and become powerful tools for probing the deepest laws of nature. Perhaps dark matter is not the simple, cold, collisionless particle we imagine in our models. Maybe it has a richer, more complex identity. Could it be a particle that can interact with itself in ways we haven't predicted, allowing it to be more easily stripped away or separated from normal matter? This opens up a vast new landscape of theoretical possibilities, a whole new dark sector of particles and forces where these strange galaxies are our only guide. They become laboratories for fundamental physics, their missing mass a clue to a deeper reality. But there is another, even more profound possibility, a theory that has lingered on the fringes of cosmology for decades, always seen as a long shot and outsider's bet. What if the reason we can't find dark matter in these galaxies is because it isn't there anywhere? What if the excess velocity in all other galaxies, the evidence that started this entire quest, is not a sign of missing matter, but a sign of missing physics? This idea is known as MOND for modified Newtonian dynamics. It suggests that our laws of gravity as laid down by Newton and refined by Einstein are incomplete. It postulates that on the vast scales of galaxies where gravitational acceleration is incredibly weak, gravity itself behaves differently. It becomes stronger than our current laws predict. This enhanced gravity would explain why galaxies rotate too fast, without the need for any invisible matter at all. For years, MON struggled to explain phenomena like the bullet cluster, where dark matter and normal matter appear to physically separate. But in a strange twist of fate, the theory seemed to predict the very existence of galaxies like DF2 and DF4. If a galaxy's internal accelerations from its stars alone were high enough, it wouldn't need a boost from modified gravity. It could exist as a purely Newtonian system, its motions explained by its visible mass alone. In the context of Monde, a galaxy without dark matter is not an impossibility. It is an expected outcome of the theory. And so these pale, ethereal ghosts discovered at the edge of visibility have suddenly become the arbiters in one of the most fundamental debates in all of science. They stand at a cosmic crossroads. Are they evidence of extreme galactic violence confirming our standard model in a strange new way? Or are they the first definitive cracks in that model's foundation? Are they telling us that dark matter is more complex and mysterious than we ever dreamed? Or are they whispering that it is a phantom itself, a ghost we invented to hide our ignorance of a deeper, more elegant law of gravity? Every new observation of these galaxies is now weighted with the fate of our cosmological understanding. We have peered into the abyss and found objects that by all rights should not exist. The universe is showing us that its rulebook is far more subtle and surprising than we ever imagined, and the page on which the true nature of these ghosts is written is still waiting to be turned. And so we found ourselves at a cosmic crossroads, caught between two elegant, powerful, and yet profoundly contradictory explanations. On one side stood the tale of the violent survivor, the cosmic orphan. This was the ultra-diffuse galaxy born of trauma, a once normal dwarf torn and stretched by the relentless gravity of a nearby giant, its stars scattered like glowing embers into a vast ethereal halo. Its diffuse nature was not a birthright, but a scar. On the other side stood a far lonelier, perhaps more tragic figure, the failed giant. This was the celestial wallflower, a galaxy born with the immense dark matter inheritance of a behemoth, yet for some mysterious reason its star formation sputtered and died almost before it began. It was a ghost, not because it was torn apart, but because it was never truly alive. A cosmic tragedy of unfulfilled potential, marooned in the lonely void. For a time the debate raged, a scientific schism that divided astronomers. Each new observation seemed to favour one story over the other, creating a dizzying back and forth. Was Dragonfly 44 a testament to arrested development, a pristine relic of a failed Milky Way? Or was it merely the victim of some long-forgotten gravitational mugging, its true nature masked by its current predicament? The evidence was compelling on both sides, and the truth seemed impossibly stubbornly out of reach. We were trying to read the biography of a ghost written in invisible ink across billions of years of cosmic history. To move forward, we needed more than just a better telescope. We needed a time machine, and in the 21st century our most powerful time machines are not built of metal and wires, but of pure mathematics and logic. We needed to build the universe again from scratch inside a computer. The solution began to crystallize not in the cold vacuum of space, but in the humming, climate-controlled server rooms that house our most ambitious cosmological simulations. These are not simple models. They are staggering feats of computation, digital universes in a box governed by the known laws of physics. Within these virtual cosmoses, we can place dark matter seed it with primordial hydrogen and helium, and then press the fast-forward button, watching as gravity patiently weaves the cosmic web over 13 billion years. We can witness the fiery birth of the first stars, the chaotic collisions of protogalaxies, the delicate dance of gas flowing along filaments of dark matter. For the first time, we had the computational power to simulate not just the broad strokes, but the fine, intricate details of galaxy formation, with enough resolution to see if something as fragile, from those first tentative detections of smudges in the darkness to the confounding paradox of a galaxy seemingly born without its soul, our journey has been one of constant surprise. We set out across the cosmic ocean in search of monsters, the colossal, the brilliant, the violent engines of creation. Instead, we found ghosts. We found whispers of starlight stretched to impossible dimensions, fragile collections of stars so sparse you could see right through them to the deeper, more ancient universe beyond. These were the ultra-diffuse galaxies, the great surprise party of modern astronomy, an invitation to a celebration of cosmic diversity we never knew was happening. Remember the initial skepticism? The first images from the Dragonfly telephoto array were dismissed by some as mere artifacts, as photographic ghosts in the machine, not celestial ones in the void. They were too large, too faint too, improbable. Galaxies we thought we understood were meant to be concentrated jewels of light, dense downtown cores of stellar activity surrounded by sprawling suburbs. They were gravitational anchors, their heft and brilliance inextricably linked. But here were structures with the size of a metropolis like our own Milky Way, yet possessing only 1% of its stars, a city of empty boulevards and vacant towers. Our voyage has taken us deep into the Virgo and Coma clusters, vast cosmic cities, where these phantoms congregate in the silent spaces between their more luminous, more aggressive neighbours. We stood before the enigma of Dragonfly 44, a ghost that defied its own form. A galaxy as vast and massive as our own, yet with 100 times fewer stars, its ethereal structure held together by an unseen skeleton of dark matter. It was a revelation, a confirmation of our deepest theories, that this invisible substance provides the scaffolding upon which all galaxies are built. Dragonfly 44 was the perfect, if extreme, example, a dark matter galaxy wearing only the thinnest, most delicate veil of stars. It was a moment of profound clarity, a sense that we were finally truly understanding the fundamental architecture of the cosmos. And then, just as we grew comfortable with this new reality, the universe, in its infinite capacity for irony, presented us with the ultimate contradiction. We journeyed to a distant galactic group 70 million light-years away to meet NGC 10052 DF2 and its sibling DF4. Here were galaxies that should not exist. Ghosts of the same size and faintness, yet when we measured their internal motions, when we looked for the gravitational glue that should be holding them together, we found nothing. The dark matter was gone. It was a cosmic crime scene with the prime suspect mysteriously absent. The discovery sent shockwaves through the astronomical community, a tremor that threatened to shake the very foundations of cosmology. How could one UDG be almost entirely dark matter, while another, its virtual twin in appearance, be completely devoid of it? It was as if we had discovered an animal with a skeleton, and then immediately found another of the same species perfectly healthy, but with no bones at all. This singular paradox has forced us to confront the humbling truth that our grand theories of galaxy formation are not complete narratives. They are merely early promising drafts. For decades the story seemed so simple, so elegant. A vast invisible halo of dark matter collapses under its own gravity, creating a deep gravitational well into which ordinary matter, cosmic gas, falls. This gas cools, condenses, and ignites into a brilliant flurry of starbirth. The density of the dark matter halo dictates the density of the galaxy that follows. It was a clean, powerful, and predictive model. Ultra-diffuse galaxies, however, refuse to read the script. They present us with a spectrum of possibilities we had never seriously considered. Perhaps they are failed galaxies born in massive dark matter halos, but whose star formation engine sputtered out almost immediately after it began. Imagine a colossal cosmic firework that, instead of exploding in a shower of light, simply fizzled, throwing off a few lonely sparks into the cavernous dark. Violent bursts of supernova explosions from the very first generation of massive stars could have acted like a celestial blowtorch, blasting the remaining gas out of the shallow gravitational well, halting any future starbirth and freezing the galaxy in an infantile diffuse state for billions of years. They would be stellar fossils, relics from a time when the universe was more violent, their expansion a permanent scar from a traumatic birth. Or maybe they are the victims of a cosmic tug-of-war. In the chaotic environment of a galaxy cluster with thousands of galaxies orbiting a common centre, tidal forces can be immense, a relentless gravitational kneading and stretching. A small compact galaxy might wander too close to a colossal neighbour, its outer layers of stars stripped away and pulled into these vast gossamer tapestries. They would not be born as ghosts, but made into them the shredded remnants of a past gravitational crime. This explanation holds a certain appeal. It explains their location within clusters and their often distorted, elongated shapes. Yet it struggles to account for the sheer number of them and for the strange isolated UDGs we're now beginning to find phantoms, haunting the lonely voids where no galactic aggressors are present? And what of the impossible ones, the galaxies with no dark matter at all? Their existence forces us to entertain even more radical ideas. Could these specific phantoms be the result of galactic collisions of a unique type, when two galaxies merge the stars and gas can interact violently, but the dark matter responding only to gravity can pass through itself like a ghost? Is it possible that a high-speed collision could separate the components, flinging out a cloud of gas and stars that is completely divorced from its dark matter anchor, a galaxy born not from a halo, but from the collateral damage of a cosmic pile-up? It is a compelling, almost cinematic explanation, but one that requires a precise and perhaps rare set of circumstances. The universe, however, is vast enough to accommodate even the rarest of phenomena. Each of these theories, the failed galaxy, the tidal remnant, the collisional debris, is a testament to the power of these ghosts to stimulate our imagination. They have fundamentally reshaped our understanding of what a galaxy can be. The neat categories we once held have been shattered. No longer are galaxies just spirals, ellipticals, and irregulars. Now there is a shadow realm, a dimension of galactic existence defined not by brightness, but by diffusion, not by density, but by deficit. They have shown us that the processes governing the birth and life of galaxies are far more complex, more chaotic, and more beautifully varied than we ever dreamed. The universe is not just a factory for producing brilliant spinning disks like our own. It is also a master artisan of the subtle, the ethereal, and the almost not there. This realization extends to the grandest mystery of all, the nature of dark matter itself. For years we have mapped its presence by its gravitational influence, tracing its invisible architecture around galaxies and clusters. It was a constant, a fundamental ingredient in the cosmic recipe. UDGs, by presenting us with both the ultimate dark matter-dominated systems and the ultimate dark matter-deficient ones, have transformed this invisible substance from a simple background component into a dynamic and perhaps even separable element of cosmic structure. They provide us with unique laboratories, paired experiments offered up by the cosmos itself. In one, we can study the behavior of stars and gas in a universe with almost only dark matter. In the other, we can study them in a universe with none. By comparing these two extremes, we can begin to untangle the intricate dance between the visible and the invisible that governs all of creation. These ghosts are not empty. They are the key. They are the control group in the grandest experiment ever conceived. And our exploration of this shadow realm is only just beginning. We have been like naturalists catching our first glimpses of a new phantom species with a small net and a flickering lantern. But a new age of discovery is dawning with new eyes preparing to open on the cosmos, promising to turn our flickering lantern into a blinding searchlight. High above us, the James Webb Space Telescope is now drifting silently through the void, its magnificent golden mirror cooled to temperatures just shy of absolute zero. Webb is a time machine. Its power lies in its sensitivity to infrared light, the ancient stretched-out light from the earliest epochs of the universe. With it, we will be able to hunt for the ancestors of today's UDGs to see if these ghosts are truly ancient relics from the dawn of time or a more recent phenomenon. Can we find diffuse infant galaxies in the cosmic nursery? Can we watch across billions of years of cosmic history as a normal galaxy is harassed and stripped into a translucent phantom? Webb will provide us not with snapshots, but with archaeology, allowing us to excavate the past and uncover the origin story of these celestial spectres. And here on Earth, on a mountaintop in Chile, a new titan of astronomy is nearing completion. The Vera C. Rubin Observatory is not like other telescopes. It is an instrument built for sheer unprecedented scale. Over the course of a decade, its enormous camera, the largest ever constructed, will survey the entire southern sky every few nights. It will produce a film of the universe, a motion picture of cosmic history cataloguing billions of galaxies and trillions of celestial events. For the study of UDGs, the Rubin Observatory will be a game changer. It will move us from the boutique study of a few dozen intriguing oddities to a full-scale cosmic census of hundreds of thousands, perhaps millions of them. We will finally have the statistics to answer the big questions. Are they more common in clusters or in the void? Do they tend to have a certain colour, a certain age, a certain shape? Are the dark matter-less ghosts a 1 in a billion fluke? or a common outcome of galactic evolution. The Rubin Observatory will drain the cosmic ocean, revealing the full, staggering diversity of life that exists in the deep, dark, quiet places. It will transform ultra-diffuse galaxies from a mystery into a population and new class of cosmic citizen, with a story to tell. With each new discovery, with every ghost catalogued by Rubin, and every ancient phantom glimpsed by Webb, we add a new piece to the mosaic. What began as a faint smudge on a digital image has become a profound intellectual journey, leading us down paths we never anticipated, forcing us to question our most cherished models. These galaxies have taught us a lesson in cosmic humility. They remind us that the universe is under no obligation to conform to our expectations, and that its most profound secrets are often hidden not in the brightest fires but in the faintest embers. They are a testament to the fact that what we see, the brilliant stars, the glowing nebulae, the majestic spiral arms, is only a sliver of the total reality. We are a species obsessed with the tangible, the bright, the loud. We build our cities with light and fill our lives with noise, but the cosmos is teaching us to appreciate the silence. It is urging us to listen to the whispers, to look for the absences, to find the meaning in the spaces between the stars. The story of the universe is not just written in the blazing hearts of suns and the violent collisions of galactic titans. It is also written in the lonely orbits of solitary stars in a galaxy of ghosts. It is whispered in the gravitational pull of matter we cannot see, and shouted in its confounding impossible absence. Our journey through this ghostly realm has shown us that the cosmos is larger, stranger, and more magical than we could have ever imagined. It's a place where galaxies can be woven from near nothingness, where the rules of formation can be bent and broken, and where the most fragile-looking objects can hold the deepest clues to the nature of existence itself. We came looking for the heart of the universe, and we found it beating not only in the fury of quasars, but in the subtle pulse of these near-invisible giants. They are the quiet sages of the cosmos, a silent, sprawling testament to the infinite creative power of the laws of nature. The great darkness is not empty, it is full of ghosts, and those ghosts are beginning to speak.